there's a train with an engine of mass of 20 tons. Calculate the speed, so we just use that. Plus 2as. We know it starts from rest, so u equals 0. V equals root 2 times acceleration 0.1 times distance 20, and that should equal to the wagon has a frictional force of 2000 newtons. Calculate the tension. So the tension is this way and the friction is this way. So then tension minus 2000 equals F net, which is, we're looking at the wagon, which is this thing, 10 tons, so 10 times 10 to the power 3, and we know the acceleration is here, so that equals to 10, 1, 2, 3 times acceleration 0.1. So then T equals 3000 newtons. And another, calculate the speed of the train. So it's moving this way. This is 0, stationary, and we're taking this as positive. So if it goes this way, it's negative. Calculate the speed after that. So then 20,000, not 20,000, 20,000 plus, that's this one when they're combined. So one system equals times V equals that one. So that's momentum, the momentum formula, that's what I used. And then V should equal meters per second. So to determine whether the collision was elastic, so to find this, we just find the energy before and after. So just half times the collision before and after of both systems. So this is U, so U is 0. So we don't need to count this, but we find this one and compare the energies. So times 20 equals 90 joules, and the EK. Joules. So therefore, because the energies are not the same, it's inelastic. It's different. Therefore, inelastic. Next part, calculate the velocity before and after. So it's moving to the right with 2 clouds, but does not couple with the stationary. So this one's going to keep moving. So M2, it's going to keep moving, and this one's going to like kind of lose velocity and just travel slower, I guess, if there's like here with M2, and this is going to be 0. So we need to calculate that, calculate the velocity after. Equals, so this is from here, and this is like from here side, and then that should equal to 1 meters per second to the right. So draw the forces on the board or the resultant force. So it's always towards the center if it's centripetal, and this is going to be the tension. This is going to be the resultant of, should probably draw it in dotted line. I get asked F R, and there's going to be weight downwards. So calculate the tension in the string. We don't know the angle, but we can use these to find the angle. So then we can say T sine 60 equals 2 times 10, and then T equals 2. Should equal 23 newtons. So now we're looking at spring with a mass of 50, but we always need it in kilograms, so 0.05. We don't know the constant, so we need to find the constant. So F equals K changing X, then K equals F changing X, which is equal to the spring is going to equal to the weight force. So then F is just the weight force, so which is M times G over change in X is this, but we need this to be in meters always, so standard units, which is 2 newtons per meter. So for this one, which is as a speed as an extension, moves from the top to the bottom. So from here to here. So the strain potential is going to be converted to the kinetic energy. So as this goes from the top to the bottom, the velocity increases until it reaches like this low point, like a parabola, I guess. And then that's going to be 0 because it's going to be like stationary. So the only one that follows that is B. It's definitely not constant. The total, this would be like the total energy would be constant, but yeah. And this doesn't make sense because it's gonna like plateau like when it reaches the bottom. So B makes the most sense. So we can just say that which increases in speed. reaches a maximum. Next part, powers of mass is 4. Comprehension by that. So the stored energy is just the area under the graph, which is just half times 0.5 times 72, which is 18 joules. Calculate the speed of the car as it leaves this. So we know the spring energy is going to be converted to kinetic. So we can equate these two. So half. We already found the value here. And we know the mass is 4. So therefore, I can just sub this in 4. So therefore, V should equal to 3 meters per second. The impulse is change in V, which is, so the M is 4 times the change in V is 2, which is 8 kilogram meters per second, or Newton second, yeah, Newton second, force times time, yeah, 8 kilogram meters per second. After the car leaves with this, it has a constant frictional of this resistance. Calculate how far before it stops. So U equals 2, V equals 0. So then 2 times distance equals half times 4 times 2 squared. So then the distance should equal to 4 meters. Calculate D when the point hits the ground. Angle of this with the speed of that. So we can use, and we know the velocity for the vertical component is acceleration is just G. And that equals to T equals to 4 seconds. So the total time from here to here is 4 seconds. And then we can use distance equals Vt. We know this is for the horizontal component. So 40 cos 30 times 4, which is equal to 1.4 times 10 to the power 2. Which of the following graphs best describe the kinetic energy of the function? So it's stationary here and it's increasing velocity. So it has to have like a parabola, parabola upwards. So that's out. That's out. And there's a non-zero flight. So it can't equal to this point here. So then it has to be A. So E and as there is so then it should correspond to A. Explain the conditions. So for it to be the same, the period, so the orbital period of the satellite is the same as Earth. And it's above the satellite is above the equator. Roger states that I feel weightless. So Emily, so you can just directly answer it because it's going to be apparent weightlessness. So Emily's incorrect. What she's talking about is absolute weightlessness, which is different. Then you just explain what it is, what is apparent. Is when an object does not feel a normal force. So then Fn equals 0. And then for the 3 marks, you could give like an example. There's like an elevator example. When a person, I guess, free falls or skydives. There is force exerted on exerted on the body. Next part. Oh, there we go. So, oh yeah, normal the North Pole is always out, so it's gonna go out and into here, into the South Pole. So just, what? How many lines? Oh, at least 4. So it just goes into here. You have to make sure that they don't intersect, because that would be wrong. And you have to make sure the arrow is like pointing correctly. So the north and the north would repel, so we just go like that. And the south would repel, but it would be like the opposite of the north, so just go in instead of out. So there's a current of this. We know the length of this conductor. And we know the force, so we can just use F equals NIBL. Force is 0.32, and then just 1. Current 2000. B we don't know. Length is 3. So then you should get B is so it says that the current is downwards. So if we're using the right hand grip rule, so your thumb would be down and it's like gripping it like this way. So then it's towards the right. So east. So according the magnetic field. So for this one, when the magnetic force on the side X from here. So when it's 0, the force is 0 is when it's like parallel to the magnetic field. So in this position it is right now, it would be 0. So the horizontal position, that is it is, and it could be like the opposite, so it could be like from Y to X. Could still be parallel to the magnetic field. So A and B. The best moves more easily when the coil in some orientations. Again, I'll explain the orientation for the stuff from moving to the rest. So it's when the magnitude of the EMF is at max. Is horizontal. So when EMF is max, EMF is max, magnetic field, whoops, mag field, no, not mag field, magnetic flux is minimum. So when it's minimum is like when it's horizontal, because there's not going to be anything going through here. Like the magnetic field is not going to go through the core. Is horizontal. And yep. I guess that's good enough for 2 marks. So to increase the speed of the rotation, increases increase the battery voltage, replace, yeah, if there's several turns, you can just according to this EMF. So if there's more turns, it's going to be more EMF. And this doesn't really do anything. Reverse one of the poles of the magnetic magnets. It doesn't really change the EMF. Increase the resistance of the coil. No, that doesn't make sense. Increase the battery voltage. Increase the, yeah. Because if you increase the voltage, then it increases the EMF. Then when there's more force, there's going to be like a greater. Speeds are A and B. You can just say according to Faraday's law. Increasing number of turns and voltage increases speed. So 15A. So the magnetic flux is BA. Oops, B capital A. Is equal to A is here. This is here. So 0.005 times 0.006, which is equal to 3 times 10 to the power -5 Webers. So it's going this way, and it's going to be 0. So the change is from here to here, and we want to oppose that change. So it's going to go from here to here, the magnetic field. So if the magnetic field is like creating its own, no, if the resistor is creating its own magnetic field in the opposite direction of this, then we can use the right-hand grip rule. So since it's going this way, you can use the right-hand grip rule and say it's like going like that. Eight second. Reduce to 0. Just go the direction of the current of the resistor. So if it's going toward the left, reduce current in the clock. Yeah. So when magnetic field decreases, flux left decreases, so the change in flux induces a current which is current that is clockwise. So therefore, it goes from Rubin Max investing in the transmission of electric power using the model as shown in figure 20A. Calculate the power delivered to globe A, so this one. So we can use P equals IV and then V equals IR. So I equals V over R. So then we can do P equals V squared over R. We know the voltage is 18. And we know that the resistance is 9. So 18 squared over 9, which is 36 watts. Calculate the voltage drop over the transmission lines. So V equals total of 3 and 9. 3 over 3 times 18. So V equals IR. Which is 4.5 volts. Calculate the power delivered to globe B. So globe B is here. So VB. So we find the difference because it's going to be lost of like the voltage. So VB is going to be 18 is the input, and we found the losses here. So minus 4.5, which is equal to 13.5. So we need to find the power, which is, do we know the resistance in B? 9. Yep. So we do the same thing we did before. So the power equals V squared over R, 13.5 squared over 9 equals 20.3 watts. So I guess 20. Yeah. So Ruby has 2 to the 1 to 10 and 10 to 1. Redraw the circuit in that with an 18 for AC and transfer current. So AC and this is the resistance in here. Step up. So and this is going here. It's going to go step down. S2 equals step down. That's gonna go connect to the globe. And this globe here is explain why the transformers would reduce the transmission loss. Your answer should include reference to key physical formulas and principle. So the step up, so using the higher the voltage, the lower the current. As the transmission lower the current, according to P equals I squared R. there is less power loss. So as there's less power loss, would reduce the... I think that's all you would need to write. Yep. Calculate the frequency, just 1 over period. So 40 times 10 to the power negative 3, which is 25 hertz. The RMS is just VP over root 2. So VP is 3.5. Root 2, which is 2.5 volts. Describe the orientations when the magnitude of EMF is maximum. So EMF is maximum. So the magnitude EMF when it is maximum is when magnetic flux is minimum. So when it's minimum, it's just horizontal. When it is maximum, is maximum when the coil is horizontal as the magnetic flux is 0. I think that should be okay. So increasing the number, so you can just use this EMF equals N change in T. So increasing this increases EMF. So increase. Increasing rotation as well increases, because it's going to be like a greater change. A greater change. If you're increasing it more, like increasing the number of turns of the coils. Increase the strength of the... So if you increase the strength, you increase B, which is found in here. So if you increase B, you increase EMF. So increase. Reduce the resistance of... Yeah, that doesn't have any effect. No effect. Doesn't change anything. Okay. So to x is here. So if we're finding the difference, so here's a bright spot. So 1, 2. So n equals 2. That's the second dark spot. So then we can do n minus half. Lambda equals 750. 2 minus half. Or I can just write 3 over 2. 3 over 2 equals 750. Therefore, wavelength equals 2 times 6 divided by 500 nanometers. So P is a bright spot. Yep. So second bright spot, n equals 2 again. But we use the whole, like multiple one. So 2 times n lambda. So 2 times 500, which is equal to 1000. So we can use the relationship between diffraction, width, and wavelength. So that's diffraction equal, I mean, not equals, but proportional to delta x. So if you change, so if you double this, so then you'll half the diffraction pattern, which is d. According to inverse of width. Say spread. Yes. Slit. 19. Emily. So we need to plot this. So 6 times 10 to the power 14. 6 times 10 to the power 14 and 0.16, which is about here, I guess. 7, 0.52, around here. 8, 0.88, around there. 9, 1.2, I guess there. So then if we should probably use a ruler for this, but that should look like that. It should look like that. Next question. Planck's constant. You can just take 2 points and find the gradient. So I will take the 2 furthest points. So 1.2 minus 0.16 over 9 minus 6, so 3 times 10 to the power 14. And you should get 3.6 times 10 to the power negative 15. And the threshold frequency, you can just look on the graph and approximate it. So it looks around 5.6. And the work function should be around here, but you can like times these two, because HF minus this is equal to EK max. So then when it's 0 equals, so then this is going to equal HF 0. So you can just times these two and you should get something around 2 volts. My graph is a bit off. Should be like that. Yeah. Explain how the recorded measurement gives information about the emitted photoelectron. So for a specific frequency, so this is basically talking about like stopping voltage and EK max. So the recorded voltage, and you need to be like specific, like they use this word, so this phrase, so you need to use it in your thing. Required. From reaching the cathode. What's the cathode in here? Did they use electrode? Yeah. This indicates the EK max of emitted photoelectrons. So increasing intensity. So increasing intensity only increases like the amount of electrons like emitted. So if you wanted to increase the kinetic energy of electrons, you would change the frequency. So it doesn't really change anything. So the second graph will be the same as the original. Then you need to talk about the wave or the particle. So it follows the particle model, because the wave model says that you could have any frequency, and like over time it should, like, the electrons should be emitted. So this supports the particle model. As EK, kinetic energy of electron, is dependent on frequency. And not DO, and I could say independent. Oops. Independent of intensity. So calculate the speed of the electrons. So we know this equals h over p, this momentum mv. So then v equals hc over lambda. So then this is always, the Planck's constant is always in joules for this formula. 6.63 negative 34. Wait, no, not hc. hm. Yep. So mv goes up to, yep. So then this is 0.36 times 10 to the power negative 9 times the mass, which is 9.1 times 10 to the power negative 31, I think, yep, which is equal to 2 times 10 to the power 6 meters per second. So calculate the energy. So we know that for it to have a similar diffraction pattern, the wavelength is like similar or the same. So E equals hf, and F is h c over lambda. So then we wanted an EV, so we used the 4.1 times 10 to the power negative 15 times 3 times 10 to the power 8 over 0.36 times 10 to the power negative 9. So then E should equal 3.5 times 10 to the power 3. Oops. EV times 10 to the power 3. So the electrons show a wave, or we could say have these and the de Broglie wavelength of each electron is the same as the wavelength of X-rays. So next question, calculate the wavelength of the emission spectral line. So we can do E equals HF, and then this is, we can, so F equals C over that. So then we can like find for this one. So over E, since it's in EVs, we know Planck's constant is going to be in EVs. Over 2.6, which is going to be 480 nanometers. Draw an arrow. So 2.6, the only one that has 2.6 is from, so 2.6, this one from here to here. And since it's an emission, so it's going to go downwards. If it was absorption, it would go upwards. There's a possible energy levels that could be. So it's excited to the 1218. So you can have, so 1218, so 1218 there, there, this one. You can have 12.8. 0.7, 2.6, 1.9, 12.1, and then 10.2. Yes, I think that's 1, 2, 3. Yep, I think that's it. Special relativity. So, and use a precise period that determine the time Barry and his clock are on Earth, and accompanies her clock on a rocket traveling at a high constant velocity past Earth towards the space lab, which is stationary. So they have identical clocks that use the precise period of aberration of this, and accompanies her clock on the rocket. So Anna's clock is going to be the same as Barry's clock, which is stationary. So the period is going to be the same. So the only one that follows that is C. So 2, when Anna is halfway between Earth and the space lab, she sends a radio pulse towards Earth and towards space lab. Observe which of the following statements correctly gives the order in which the signal by Barry is received. So as the signal is received by Barry's here and the space lab. So they're in the same, it's halfway, so for it to travel this way and that way, it would be the same. So C. Car moving towards, so it's moving towards the, so car's moving towards the loudspeaker and towards the light source. The speed of sound relative to color and the speed of light relative to Han. So light is always going to be the same, doesn't change. And because she's moving towards the loudspeaker, the speed is going to increase. It's going to be the speed of her and the speed of the loudspeaker. So it's going to be C. Michelson-Morley result. Einstein's first postulate remove the problem of nope. It did not remove that. It does not prove Maxwell's equations. Einstein's second postulate on the speed of light. Explain the Michelson-Morley result. Yeah, it's B. No, that was like rejected. The ether thing was rejected. Pions are particles that are present on this. In the frame of reference, will the undilated value of the half-life be correctly observed? In which the undilated value be correctly, so it has to be in the same, like they have to be in the same frame of reference as the pions to be correctly observed. Otherwise it's going to be like dilations and stuff. So in each pion's own frame of reference. So 6, consider each travels the speed of this. It decays with 26 that. How long did it take? So we can just use this T. And we can just simplify this because it's the C's and the C in this formula would just cancel out. So you just 0.98 squared, which is 130. C. 7. The space lab of this traveling at this speed. Apart from the space lab, how far apart are the two detectors in this particular frame of reference? So the contracted length is going to be 2 over 2.4. So 2 meters, 2 which is going to be 0.83 meters. Eight. The time taken for the acceleration in the particle's own frame. So it's in its own frame of reference. So the linear accelerator is used to increase the speed of this. The particle is accelerated from 2 to this. The particle reaches a speed at which this is this. The time taken for this acceleration because it's being accelerated, because special relativity only applies to non-accelerated objects, so we can't really do anything. So it's 8D, I think. 9 from rest. So rest energy of this, the value of this reached. So this is going to be equal to 1 mc squared. So 1.2 times 10 to the power of negative 10 over mass is 1.67 times 10 to the power of negative 27. Speed of light 3 times 10 to the power of 8. And we square this. So 10, which is gonna be approximately, let me just check. Approximately 1.8. So question 10. With this collides with the stationary and the rest of the proton, which is the kinetic energy after the collision. So we just use the conservation again, like we did before. So mc squared equals, so the energy kinetic energy. So then we start off with this, so 3 minus 1 m equals 2m c squared plus ek. So then bring this on the other side, so ek equals 1 mc squared. So then should be 11. The specimens describe the speed of light in the various medium, including. So light is like, it has this electrical and magnetic, like it's like perpendicular to each other. It's hard to draw. It's like this. It's like perpendicular, and it only depends on that. So it's like independent of the material itself. So 11 is C.
Thank you.
Oh, good.